Welcome to your online class. This is Bilal Khan from Peshawar Public School and College. Let's begin our lesson of the day. We have been discussing organic chemistry and organic compounds. We know that organic compounds are the compounds of carbon and hydrogen. They are carbon-based compounds. Uh, these compounds occur in the form of molecules of carbon and hydrogen. These molecules uh, form long chains, and the main skeleton of these molecules is formed by carbon atoms. Carbon atoms have a property called catenation. Let me write it here. Um, Catenation. Catenation is the property of carbon atom to form long chains. This is why there is so many organic compounds. Uh, they occur in the form of long chains. This property of carbon atoms is called catenation. So our today's lesson is about the bonding in organic compounds. We are going to see how bonding occurs in organic compounds, uh, how carbon atoms form bonds with each other and with other atoms, and how so many uh, organic compounds are formed. In order to understand the bonding process of organic compounds, uh, we need to understand what hybridization is. Here we have got this hybridization, so we are going to look into it. We are going to see what hybridization is, how hybridization can explain the tetravalency of carbon atoms, how it can help us understand the process of bonding in organic compounds. So let's go into hybridization. According to this definition, hybridization is the mixing of atomic orbitals into new hybrid orbitals suitable for the pairing of electrons to form chemical bonds. According to hybridization, atomic orbitals which are very slightly different in energy, they will come together, they will mix with each other, and they will give rise to a completely new set of hybridized orbitals. It can be shown as a diagram. Let's say this is the atomic orbital S. This is the energy. This is, here we have the atomic orbitals Px, Py, and Pz. You can see there is a very little energy difference between these two orbitals. So it is possible that the s orbital and the three p orbitals mix with each other, and they give rise to completely different orbitals. Four different orbitals. These orbitals have the same shape, the same geometry, the same energy. They are degenerate. Degenerate means orbitals that have the same energy. all these orbitals have got same energy on this energy curve. You can see they lie on the same position. This is how hybridization occurs. Before we go into the detail of hybridization, it's important to discuss the electronic configuration of carbon atom. Carbon atom has a total of 6 electrons. The 6 electrons can be arranged like this: 1s2, 2s2, 2p2. Diagrammatically, it can be represented like this. The 1s orbital is the lowest energy orbital. Then you have the 2s, and then you have the 2p orbital. The 2p orbital has got 3 orientations. Alright, so it can be divided into 3 components: the 2px, the 2py, and the 2pz component. There is a total of 6 electrons. So according to the Aufbau principle, the filling of electron occurs like this, from lower energy orbital to the higher energy orbital. We have got a total of 2 unpaired electrons in carbon atoms. But what we see is that in methane, carbon atoms form 4 bonds. This tetravalency of carbon atom can be explained on the basis of hybridization. According to the theory of hybridization, 1s and 3p orbitals will combine to form 4 sp3 hybridized orbitals. One s from here and 3p orbitals from here are going to mix with each other, and they will give rise to a completely new set of hybridized orbitals. The sp3 hybridized orbitals. They're degenerate. They have got the same energy. So each of the sp3 hybridized orbital has got 25% s character and 75% p character. Let's explain this a little further. This is the electronic configuration of carbon atom in the ground state. In the ground state, it has got only 2 unpaired electrons, one in the px and another in the py. The electron can be excited from this 2s orbital. One of the electrons can be excited from this 2s orbital into the 2pz, which lies vacant. So now you have 4 orbitals. Now you got 4 orbitals, all with 1 unpaired electron. In the next step, these atomic orbitals are going to come close to each other, mix into each other, or merge into each other, and they will give rise to a completely different set of atomic orbitals. The sp3 atomic orbitals. This is how hybridization happens. In the ground state, the electronic configuration can be shown or represented by this diagram, and this is what happens after hybridization. So you have got 4 degenerate sp3 hybridized orbitals, each with one unpaired electron. Each orbital is going to fulfill its valency, is going to get another electron. That is why carbon atom has this tetravalency. It forms 4 bonds rather than 2 bonds. Let's talk about a little bit about valency, because without a prior knowledge of valency, you cannot grasp the concept of hybridization. So valency is the number of unpaired electrons in the outermost shell of an atom. Elements of the same group have the same valency. Elements of the same group of the periodic table have the same valency. Valency can be found from the electronic configuration of carbon of atom. If you want to find out the valency of any atom, all you have to do is just write down the electronic configuration and find out the number of unpaired electrons. For example, here hydrogen has got only 1 electron, so its valency is 1. Sodium has got a total of 11 electrons. If you arrange these electrons according to the principles of quantum mechanics that you have already studied in your previous class, you can arrange these electrons just like this. So you get an unpaired electron in the 3s orbital. Its valency is 1. It can form only 1 bond. It loses only 1 electron. It forms ionic bond, so it loses 1 electron. This is the first A group of the periodic table. The group number represents the number of unpaired electrons in carbon atom or any atoms. In beryllium, you have 2 electrons. In magnesium, you have 2 electrons in the outermost shell. So they belong to the group 2nd A. Here we have 3 electrons. 3 electrons in the outermost shell. So this belongs to the group 3rd A. And the next one, carbon. Carbon has got a total of 6 electrons. If you arrange these electrons according to the principles outlined by quantum mechanics, this is what you get. This is what you get. You get only 2 electrons in the outermost shell, but the p orbital has got 3 components: px, py, and pz. So one of the electron can be excited from here and it can move here. So you will have a total of 4 electrons, 4 unpaired electrons. So it is group 4A. This is the valency table. It shows the valencies of different atoms. The valency of an atom corresponds to its group number. Group number 1, all elements of group number 1 have the valency 1. All elements of group 2 have the valency 2. All elements of group 3 have the valency of 3. All elements of group 4 have the valency of 4. Elements of group 5 show a valency of 3. Elements of group 6 shows the valency of 2. That is why in a molecule of water, Oxygen has the valency of 2 because it belongs to group 6. It has got only 2 unpaired electrons in the outermost shell. The group number and the number of unpaired electrons correspond with each other. Group 7 has the electronic configuration of, if you take an element from group 7, for example, you can take chlorine or fluorine, you can do the electronic configuration, and what you see is that like if it is fluorine, F9, it is going to be 1s2, 2s2, 2p, 2p5. So it has got only one unpaired electron in the outermost shell. This is how the electronic configuration shows the valency of an atom. So according to the concept of valency, carbon atom should form 2 bonds because it has got 2 electrons in the outermost shell, but it forms 4 bonds. So we need another theory. We need a theory to explain the tetravalency of carbon atoms, the property of catenation found in carbon atoms. And this is explained on the basis of hybridization. What happens in hybridization is very simple. Let's repeat this again. The s orbital and the p orbitals, they have a very little energy difference. So they can mix with each other. As a result, they will give rise to a completely different set of orbitals. These orbitals will be different from their parent orbitals. Their shapes will be different, their orientation will be different, their geometry will be different, their energy will be different. For example, as you already know, the s orbital is spherical. This is the s orbital. And the p orbital is dumbbell shaped. This is the p orbital. Now if you mix them together, you will get a hybrid orbital. It's going to be like this. 75% of this orbital is like the p orbital, and 25% is like the s orbital. So it has got the characteristics of both p and s orbitals. What happens is that carbon atom will undergo this hybridization, and it will give rise to 4 sp3 hybridized orbitals, which are arranged like this. The angle between these orbitals is 109.08 degrees. They arrange themselves along the corners of a tetrahedron. So this is the theory of hybridization, and with the help of this theory we can explain why carbon atom forms 4 bonds rather than 2 bonds, and why there is such a diversity in organic compounds, why there is this property of catenation. I think this much is enough for today's lesson. Thank you very much.